and it's found in a work by an Austrian philosopher from 1912. And the way you formalize it is you introduce this notation, x to the left of f, whereas in standard logic, you also keep the standard notion of predication, x1 through xn exemplify the relation fn, right? So I'm going to build a formalism that extends classical logic with a new kind of predication and use that to give my theory. And you can find this distinction in other philosophers as well. Boulos and Kripke have versions of it, but it's not formal in their work. So let me give you some examples. What is the Platonic form of the triangle? What is pure triangularity? The triangle, when we say the triangle has 3 sides, or the triangle has interior angles summing to 180 degrees. I'm not talking about a particular triangle. I'm not talking about a physical object. I'm talking about somehow this Platonic ideal. And what that's going to end up being on my theory is it encodes all and only the properties that are necessarily implied by the property of being a triangle. So you take the property of being a triangle, it implies having 3 sides, having 3 interior angles, having interior angles summing to 180 degrees. You take all the properties implied by that, and it doesn't imply whether it's equilateral or whether it's isosceles. It just implies the things implied by being a triangle, and you build an object out of that. That's your conception of the triangle, and my system will then formalize that as a specific object in the domain. Similarly, the Dedekind piano number 1 is going to encode its mathematical properties that are given by the axioms of Dedekind piano number theory. So each abstract object is going to encode a unique group of properties. And the way I formalize this is I take a predicate for being abstract. This predicate here is the A with a bang with an exclamation point. And you read that x is abstract. And this backwards E with the exclamation point means there is a unique thing, x such that phi. So then I'm going to assert that for any properties satisfying, this is now a schema that has an infinite number of instances depending on what formula you put here for phi. If phi is any formula that has a condition on this free variable f, then the result is a statement that's an axiom of the theory of abstract objects. It asserts there is an abstract object that encodes all and only those properties f that satisfy phi. Okay? So there's going to be, and in fact there's going to be a unique one because 2 abstract objects are going to be identical whenever they encode the same property. So that means that this definite description is canonical. It always has a denotation no matter what you put in for phi. There's always going to be a corresponding instance of comprehension that asserts that there's a unique such thing, right? So we can skip the idea. There are paradoxes lurking, but I've taken steps to avoid paradoxes. So how is this kind of theory going to help us? Well, I'm going to have to move quickly now because I'm running out of time. Suppose the is of natural language predication is ambiguous between 2 kinds of predication. X is f means either x exemplifies f or x encodes f. Well, then if you take G necessarily implies f, this is how you express that in modal logic, then the form of the triangle becomes this. Remember, the form of the triangle is the abstract object that encodes all of those properties f that are necessarily implied by being a triangle. So you can write that down. And you can do that now for any property that a theory encodes, all right? So phi sub t is going to be the form of the triangle. Okay, so let me skip this and move on. So here's an example of piano. So now take piano number theory or piano arithmetic. What does the symbol, the numeral 1 symbol in piano arithmetic mean? Well, you basically say, you take all the theorems of piano arithmetic, look at all the properties of the number 1 in those theorems. All the properties, what are those properties? Being such that it's greater than 0, being such that it's less than 2, being such that it's not prime, it's the one before the first prime number, blah, blah. It's being such that it's odd. You take all those properties and you encode them into an object. That abstracts out an object that we can now say is what the numeral 1 means in piano arithmetic, okay? That allows us to distinguish the properties, excuse me, the properties that the number 1 encodes from the one it exemplifies. Now I can say the number 1 encodes only its mathematical properties. That's what this tells us. But it exemplifies not being red, not being colored, not having a shape. It exemplifies for every property either it or its negation. So it's complete with respect to the properties it exemplifies, but it's incomplete with respect to the properties it encodes because it only encodes mathematical properties, okay? So that's the general picture. You can supply, and I'll show you now quickly, you take any theory T, take your favorite mathematical theory T, and take the theorems of T, and whenever you've got an axiom or a theorem of theory T, you add to object theory this fact that T encodes being such that phi, where this symbol here is defined as T. Now the theory T itself is an abstract object because it's a body of content, it's a body of propositions, and it encodes the property being such that P, where P is a proposition here, and that way you can take as a reduction axiom the following principles. You can say, look, take any constant in T, 0 of piano number theory, the null set of ZF. Those are constants of T. And you can identify them with the properties that they have in their respective theories. So you get, as a consequence, that the constant in question encodes a property if and only if it exemplifies the property in T. Now this helps to really give us an interpretation. This formalism now works for an arbitrary mathematical theory. Now, each different way of interpreting the formalism gives us a precise way of understanding one of those philosophies of mathematics. Clearly, we've already got Platonism, and I'm going to skip this slide. So we've already got Platonism because the terms of mathematical theories denote abstract objects and relations. Platonism comes for free, so I'm going to skip that one. What about logicism? Well, logicism says mathematics is reducible to logic and analytic truths, but of course that doesn't work because logic is typically weak, whereas mathematical theories have very strong existence claims. So you might wonder, why was logicism ever a viable option? And in this case, the idea here is that object theory gives us a new kind of reduction. The terms and predicates of mathematical theories are given denotations because what those objects are that I postulated with that comprehension principle, they become logical objects. That is, they simply embody the freedom that we have in formulating conceptions of mathematical entities, or any kind of entity, by way of their properties. So this is a kind of capturing the logic underlying consciousness. We are free in our conscious thoughts to formulate any sort of theory about mathematical objects, and what that gives us is a kind of logical principle for generating objects to capture those states of consciousness that are about specific mathematical things. And I'm working on a paper now thank you. I'm working on a paper with others to try to make this more precise. Now, I'll quickly say that this gives us structuralism the way Dedekind wanted it, because Dedekind, remember, wanted objects whose only properties were their mathematical properties, and here we've got a reading for that. We've also, these special objects that encode and exemplify properties, they do encode only their mathematical properties. Of course, they exemplify properties as well, but that's okay. Dedekind simply said you need to have objects whose only properties were their mathematical ones, and that is captured. And this gives us readings for something that Paul Benassareff said he said, in giving the properties of numbers, you merely characterize an abstract structure. And the distinction lies in the fact that the elements of the structure have no properties other than those relating them to other elements of the structure. And here we've got objects whose encoded properties are only the properties relating them to the other elements of the structure. So we get structuralism. Inferentialism. Remember, what I did was I started with the principles. I took the axioms and theorems, and then I reduced them by turning the theorems with a single line into analytic truths of this form. And so no matter what mathematical object you're interested in, you can abstract its inferential role and turn it into an object. We're reifying the inferential role of each mathematical term. And that somehow is a way of, I think, is a way of understanding inferentialism as a theory. Formalism. What about formalism? Well, very quickly. The formalists say mathematics is a game by manipulating formal symbols. But what are symbols? Of course, if you want to talk about symbols, you have to invoke the type-token distinction. If I ask you, how many letters are printed on the next line? How many letters are on that line? Well, there's two possible answers. There's only one letter printed, namely the letter A, or you could say there are two letters printed, namely the letter A on the left and the letter A on the right. But a better solution is to say, look, there's one type of letter, the A, the letter type A, and there are two tokens of the letter A there. So when Hilbert and others talk about formalism, they're not talking about the tokens. Mathematics is not about physical inscriptions on the page. They're about types of things, mathematical symbol types. And those are abstract, and we have a way of understanding the type-token distinction. Is the types encode the properties that the tokens exemplify. Okay, finally, I'll move on to fictionalism. And fictionalism is basically, you get that for free by reinterpreting the quantifier. There is, this backwards E can be read there is, not there exists. Of course, Quine told us that we have to read it as there exists, but I don't think we have to do that. I think we can simply read it as there is without implying existence. And so you then get a reading on which these abstract objects are not possibly concrete things, but rather not the kind of thing that could exist. So the numbers become non-existent things. That's a kind of fictional view about mathematics. But you get that for free as an interpretation of the formalism by reinterpreting what the primitive terms and the formalism mean, okay? So I'll skip that. So let me summarize. Last slide. Different philosophical interpretations of a formal framework and its analysis give us the different philosophies of mathematics. I gave you a formal framework. I showed you how it can describe abstract objects generally and how any arbitrary mathematical theory can be interpreted in that framework. But then we gave an interpretation of that framework, many different ones, and those captured the philosophies of mathematics. So that means that in many ways, all those different philosophies of mathematics become unified by a single formal framework. And that's the idea behind this talk. So this explains why the different philosophers of mathematics can't even agree on the data. Basically, the Platonists who think mathematics is true and the fictionalists who think it's false, they're looking basically at the same formalism in mind, but they have different interpretations of that formalism. And on one, the Platonists are focusing on the encoding readings, which are true, and the fictionalists are focusing on the exemplification readings, which are false. So this explains mathematical and metaphysical incompleteness, because the incompleteness comes on the encoding side, not on the exemplification side. And now we can explain knowledge, because knowledge all reduces to descriptions. Descriptions anchored in a theory. All you have to do to get into contact, get your mind into contact with an abstract object, is to understand its defining description. All of those objects that I identified earlier in the talk, they have a unique canonical description saying which object in that domain they are. So knowledge is by description, not by acquaintance. We don't need some special information pathway in order to access the numbers. And I didn't talk much about Carnap, so I'll skip the last bullet point. So let me stop there and say that that's how I want to present a unified way of thinking about the philosophy of mathematics, in which all these other different balkanized views about the philosophy of mathematics can all be grouped together using one formalism. Thank you very much. So there should be time for questions now.
Thank you so much, sir. Now the forum is open. You can ask any question what is in your mind right now.
Yes, I would like to ask a question. But first of all, this was a very, very interesting talk, and the subject was completely new to me, so I'm not going to ask any technical questions.
Sure.
But I think I interpret your talk in the right way when I say that you consider mathematics as a product of the human mind.
I don't know whether I go that far. I would say that whatever mathematics is, in order for us to understand it, we have to make our own conceptions of the things in question. It may turn out, so I didn't commit myself to any of those particular philosophies of mathematics.
I know.
There might be one that's distinguished, and so for all I know, right, it could be that those mathematical theories are, in some sense, one of those interpretations is the preferred one. But I didn't commit myself to which one is the preferred.
No, but that's where I'm heading, of course. The next question is then, does mathematics refer to an external reality?
Yes, I think it does. And what I think they are is basically patterns in nature.
Okay.
Patterns that are possibly connected with consciousness.
Okay.
Because when mathematicians so here's the idea. In order for a piece of language to be meaningful, it's got to be used in a systematic manner by multiple people. If there's not a systematic usage, then as Wittgenstein told us, there's no meaning there, right? If it's a random usage, it couldn't be meaningful. So when mathematicians all agree on some axioms and they set up a community, there's a pattern that emerges of speech, a pattern of language. And what I've given you is a way of abstracting out objects from the subsentential patterns of the language that's shared by the community of mathematicians.
Okay, then my last question. The problem of Platonism is indeed, as you indicated, how does our mind get in touch with these transcendental objects or structures, or however you want to call them? Well, there is, of course, Balaguer's solution, the full-blooded Platonism. How do you feel about that?
Balaguer's full-blooded solution was published 2 years after Linsky and I published the very same theory. We called it principled Platonism in 1994. His book came out in 98. And he referenced it, but he didn't show the connections. The problem with so there's a difference though. So that comprehension principle I gave you is completely unrestricted. It's a plenitude principle. Balaguer's full-blooded Platonism is a plenitude principle. But the problem that Balaguer has is every object for him only has one dimension on which it has properties. So it's complete and determinate down to the last detail.
Okay.
So he can't tell you, does the null set of the Zermelo set theory denote the null set, an object such that the continuum hypothesis is true or the continuum hypothesis is false? For Balaguer, both of those objects are in there, but he can't get you from the theory to one of those unique objects. Whereas, because we distinguish between two kinds of predications, the Zermelo set theory puts us to a unique object that only encodes the properties of Zermelo-Frankel set theory, and continuum hypothesis is not part of it.
Okay.
So there's a very big difference, yes.
Thank you.
They're
Lovely
theories,
talk.
yes. It's a good question. It's a good question, but people
Thank
don't
you
know
so
that
much.
there's
Anyone more?
Christoph, I see.
Thank you very much for your thought-provoking talk. But your very first premise is based on semiotics, the theory of symbols. Am I right? Do you hear me?
I
No?
hear you, but I'm not sure I understand the question. I'm using symbols, yes.
The very first premise started with the very first premise that a symbol has a meaning that you have embedded in it, nothing more.
I think the symbol acquires meaning through a systematic usage in the language.
The semiotics says a symbol has no meaning except that the one you ascribe to it.
Okay, how do you ascribe meaning to it?
Yeah,
By
yes.
using it in a systematic way. And if you, not random.
That's what you talked about, the community of mathematicians. They use in a systematic way. The second thing is you have used an expression, analytic truth. Is it a camouflage of logical truth?
Sorry, what was the,
You have used an expression in your talk,
yes.
analytic truth.
Analytic truth, yes.
Is it camouflage of logical truth?
So typically, the logical truths form a subset of the analytic truths. That's the way most people use the term. For example, it's an analytic truth that all bachelors are unmarried. But that's not a logical truth because bachelor is not a typical logical term. So there's a class of analytic truths that aren't logical truths, but all logical truths are supposed to be some form of analytic truth because they are true in virtue of the meaning of the logical words, not just the meanings of the general words.
No, I think I do differ because any analytical truth has to play on the playground of its domain. The mathematics plays not in the real world. Russell has already said it. If all men are mortal and Socrates is a man, Socrates dies.
So I don't presuppose any model theory. In order to make your claim, you have to presuppose a lot of mathematics.
Right.
But that's precisely what's in question.
But analytical truth is different from logical truth, you say. But mathematics binds itself to a logical truth on the assumptions or axioms it had already made.
Well,
It doesn't care whether Socrates is a man or not. If
Sure.
all men are mortal and Socrates is a man,
Yes.
Socrates has to be mortal. Whether Socrates is a man or not, it's bother.
Absolutely. I certainly agree. I don't see any inconsistency there with that.
So there is no analytical truth in a mathematical system beyond a logical truth accepted by the mathematics.
Well, the only way which I used the analytic truths in my system was to say, here's an analytic truth. In ZF, the null set is a set. I took the axioms of ZF, put them under the scope of the theory operator in ZF, and that, I claim, is an analytic truth about what ZF is. Yeah.
I ask my students this question. How many color...
I think we should I'm sorry, we should let somebody else because we could go
So
on.
let me excuse. Any further questions we can discuss in personal discussion. Thank you so much. So let's follow Rai for the next schedule. And over to Shubham.
Okay, sounds like we don't have any more time.
Thank you so much. Thank you so much, Dr. Edward and Zalta. It was nice to have you on the dais. Thank you very much once again. Ladies and gentlemen, can you please put your hands together for Mr. Edward Zalta? You know, we had a great journey, we are doing a great journey towards the reality from mathematics, right? We are connecting everything, or we can say that we are trying to connect everything in a very particular time. But now it's a high time to showcase something very cultural to you all. It's entertainment time, and for that would like to welcome to the stage from Amrita Vidyalaya, Odissi, Mangalacharan, under the guidance of Mrs. Malvika Das. So ladies and gentlemen, please put your hands together and let's welcome all the performers right there on the stage.